This address resolution protocol was originally designed for the DEC, Intel, and Xerox 10 megabit Ethernet. It has been generalized to allow it to be used for other types of networks. For ease of understanding, let us assume the implementation of protocol P on a sending host S decides through protocol P's routing mechanism that it wants to transmit to a target host T located someplace on a connected piece of 100 megabit Ethernet cable. To actually transmit the Ethernet packet, a 48-bit Ethernet address must be generated. The addresses of hosts within protocol P are not always compatible with the corresponding Ethernet address. In this type is a protocol that allows dynamic distribution of the information needed to build tables to translate an address A in protocol P's address space into a 48-bit Ethernet address. Generalizations have been made which allow the protocol to be used for non-10 megabit Ethernet hardware. Some packet radio networks are examples of such hardware. Consider the world is a jungle in general, and the networking game contributes many animals. At nearly every layer of a network architecture, there are several potential protocols that could be used. For example, at a high level, there is Telnet and SUPDUP for remote login. Somewhere below that, there is a reliable byte stream protocol, which might be CHAOS protocol, DOD-TCP, Xerox BSP, or DECnet. Even closer to the hardware is the logical transport layer, which might be CHAOS, DOD Internet, Xerox PUP, or DECnet. The 10 megabit Ethernet allows all of these protocols and more to coexist on a single cable by means of a type field in the Ethernet packet header. However, the 10 megabit Ethernet requires 48-bit addresses on the physical cable. Yet most protocol addresses are not 48 bits long, nor do they necessarily have any relationship to the 48-bit Ethernet address of the hardware. For example, CHAOS addresses are 16 bits, DoD Internet addresses are 32 bits, and Xerox PUP addresses are 8 bits. A protocol is needed to dynamically distribute the correspondence between a protocol and address pair and a 48-bit Ethernet address. Now let us brief why ARP needed. Use of the 10 megabit Ethernet is increasing as more manufacturers supply interfaces that conform to specification published by DEC, Intel, and Xerox. With this increasing availability, more and more software is being written for these interfaces. There are two alternatives. 1. Every implementer invents his or her own method to do some form of address resolution. Or second, every implementer uses a standard so that his or her code can be distributed to other systems without need for modification. This proposal attempts to set a standard to communicate mappings from protocol and address pairs to 48-bit Ethernet addresses, a packet format that embodies the address resolution protocol is needed. Let us look ARP detailed concept. ARP is used on IEEE 802 networks as well as on the older Dix Ethernet networks to map IP addresses to physical hardware addresses. To do this, it is closely related to the device driver for that network. In fact, the ARP specifications in RFC 826 only describe its functionality and not its implementation. The implementation depends to a large extent on the device driver for a network type, and they are usually coded together in the adapter microcode. ARP packet generation. If an application wants to send data to a certain IP destination address, the IP routing mechanism first determines the IP address of the next hop of the packet. It can be the destination host itself or a router, and the hardware device on which it should be sent. If it is an IEEE 802.3 or 4 or 5 network, the ARP module must be consulted to map the protocol type target protocol address to a physical address. The ARP module tries to find the address in this ARP cache. If it finds the matching pair, it gives the corresponding 48-bit physical address back to the caller, which then transmits the packet. If it does not find the pair in its table, it discards the packet, assuming that higher level protocol will retransmit, and generates a network broadcast of an ARP request as shown in the figure. Referring to the figure, 1. Hardware address space and specify the type of hardware. Examples are Ethernet or packet radio net. Second, protocol address space and specifies the type of protocol, same as the ether type field in IEEE 802 header. Third, hardware address length and specifies the length in bytes of the hardware addresses in this packet. For IEEE 802.3 and IEEE 802.5, this is 6. Fourth, protocol address length specifies the length in bytes of the protocol addresses in this packet. For IP, this is 4. Fifth, operation code, and specifies whether this is an ARP request 1 or reply 2. Sixth, source or target hardware address, and contains the physical network hardware addresses. For IEEE 802.3, these are 48-bit addresses. And seventh is source or target protocol address, and contains the protocol addresses. For TCP/IP, these are 32-bit IP addresses. For the ARP request packet, the target hardware address is the only undefined field in the packet. ARP packet reception. When a host receives an ARP packet, either a broadcast request or a point-to-point reply, the receiving device driver passes the packet to the ARP module, which treats it as shown in the figure. The requesting host will receive this ARP reply and will follow the same algorithm to treat it. As a result of this, the triplet, that is protocol type, protocol address, and hardware address for the desired host will be added to its lookup table, that is ARP cache. The next time a higher level protocol wants to send a packet to that host, the ARP module will find the target hardware address and the packet will be sent to that host. Note that because the original ARP request was a broadcast in the network, all hosts on that network will have updated the sender's hardware address in their table. ARP and subnets. The ARP protocol remains unchanged in the presence of subnets. Remember that each IP datagram first goes through the IP routing algorithm. This algorithm selects the hardware device driver that should send out the packet. Only then the ARP module associated with that device driver is consulted.